IBS bridge structure was selected by the Maine Department of Transportation for the Bremen site to reduce construction time and costs and to test a new technology that is part of the Federal Highways Every Day Counts initiative. The Bremen site is the first location it has been used in Maine. This technology uses alternating layers of compacted fill material and fabric sheets of geotextile reinforcement to provide support for the bridge.
The structure itself, we're all quite excited. It's one of the first, maybe the first one in Maine, GRS IBS system for building a bridge, and we want to see how it works. It's been used a lot in other states, and so it's always good to try something new. And we're hoping it might provide an efficient, cost-effective, easy-to-build solution for open-bottom structures.
Construction benefits. This simplified bridge building process can greatly reduce construction time. A GRS IBS is built in days or weeks, not months. There is no need to wait for cast-in-place concrete to dry. The substructure is immediately ready for the structural span, and on-site changes are easy to accommodate. This lower-tech option can also reduce material costs. Inexpensive, common materials and equipment are used. There is no need for highly skilled labor. The GRS part of the project consists of building the facing retaining wall and the soil work behind the wall. A simpler construction also means simpler maintenance. While a GRS IBS bridge can be simpler and less expensive to build than a traditional span, it must still meet the site requirements of any bridge. In particular, when used as a water crossing, it must be engineered to be scour resistant.
It's like a giant set of Lego blocks. You know, everything's precast, everything locks in together, and you just start building on top of one another, and then the concrete deck panel spans over what we've built for abutments. So the only concrete work that's cast in place is the footers, which act as the anchor and the leveling pad for the concrete abutments.
Water control. Water control typically consists of diverting all existing stream flow around or through the working area of the construction site, keeping any of the stream flow clean as it passes through the crossing area.
The actual dimensions of the stream will be 14 feet wide. The pipe that's there now is 4-foot diameter pipe, so we're able to actually work on the abutments and keep the existing pipe in the ground and let the water flow through the pipe while we do that side work. And then what we'll do is we'll wind up blocking up the stream, taking that pipe out, and then we'll actually see what that ledge looks like for that natural bottom, and to see if we need to do any fish weirs or not, because lots of times if the ledge is irregular enough, it'll hold those pockets of water that essentially what a fish weir would simulate.
At the end of the construction process, when removing the existing pipe, the clean stream water was pumped around the construction site, and any remaining dirty water in the work area was pumped into a sediment basin. Erosion control and wide sandbag cofferdams were set up to ensure stability and to minimize the amount of dirty water created during construction from subsurface upwelling and unexpected rain events. Because the surface was uneven ledge and rocky, rocks were removed in order to get as good a seal as possible, but were placed back in the stream after construction because they are part of the stream structure and are habitat for aquatic life. A good seal was created using 6mm poly underneath the cofferdam. A sediment basin was built using a group of hay bales to create walls and lined with a non-woven geotextile. Stakes were driven through the hay bales to give it structural integrity to handle the weight of water. The dirty water was then pumped up from the site into the basin to catch the fine sediment. A mat of fine soils left on the fabric was disposed of when the project was done. The pump size was chosen based on how high up the water had to be pumped to the sediment basin. To prevent fish and aquatic life from getting trapped by the pump, an intake screen was put on the uptake of the pump. It was constructed using a 5-gallon bucket drilled with holes about 3/4 to 1 inch diameter throughout the pail, and then soft window screen about 1/32 of an inch opening wrapped around the pail and anchored down with duct tape. They put the large 6-inch pump intake in the pail and kept the level of the pail above the water level so nothing could get into the pump that couldn't go through the screen.
In this particular location, there isn't a lot of organic material coming down through this system, at least not this time of year, so we didn't have a lot of material getting stuck against the screen. If you're in a place where you have a lot of organic material, oftentimes a contractor will build his screen much bigger so that he has a lot bigger surface area, so that because that suction is going to be pulling all that stuff against it, so they don't lose their prime on that pump.
Multiple people were on hand to manage the water, refuel the pumps, check pump intakes to make sure the screens were not clogging, and to make sure the sediment basin did not overtop. Before removing the existing pipe and allowing water to flow through the new channel, as much of the sediment as possible was removed from the exposed ledge using hand tools and washing the ledge. Geosynthetic reinforced soil, GRS. Rather than drilling a deep foundation, the reinforced soil method builds up the substructure in a faster, simpler way. In some respects, it is similar to building a layer cake. First, builders lay a row of facing blocks. Second, they add a layer of compacted fill, or the cake, 8 inches to the height of the facing blocks behind the facing. Next, they add a layer of geosynthetic fabric, or the frosting between the cake layers. This 1-2-3 process is repeated over and over until the desired height is achieved. Each layer of geosynthetic fabric is extended between the rows of blocks to frictionally connect the block to the GRS mass. Two critical aspects of this fundamentally simple technique are that the layers be thin, 8 inches, and well compacted. The effect of the geotextile is to reinforce and strengthen the soil. GRS is an internally supported system, which means that it stabilizes the soil mass simply by including reinforcement sheets. The tightly spaced reinforcement in granular soil create an internally stabilized composite material. Face wall abutment. The bridge at Bremen, Maine uses a simple concrete retaining wall in place of a GRS block wall. Because GRS facing blocks are primarily used as a construction aid, different facing types can be used. The GRS behind the facing carries the bridge load and functions as an abutment. The wall provides a form for each lift of compacted fill and serves as a protective barrier. The wall is similar to a simple concrete house foundation wall, as opposed to a more complicated and expensive bridge abutment. Bridge beam and deck. The bridge structure is placed directly on the GRS abutment mass. A GRS approachway is built behind the bridge beams to transition the bridge to the approaching roadway. No joint or cast-in-place concrete is needed. The bridge extends naturally out of the roadway. GRS provides a smooth transition from the bridge onto the roadway and alleviates the bump at the bridge problem caused by uneven settlement between the bridge and approaching roadway. The integrated bridge system is typically built without many of the elements common to a conventional bridge abutment, such as the deep foundation, bridge seat, bridge bearings, deck joints, approach slab, end wall, and sleeper slab. Post-construction conditions.
So we went from a 4-foot wide pipe to a 14-foot wide bridge opening, and that is a consideration not only for fish and wildlife passage, but also would increase the hydraulic capacity so that there wouldn't be overtopping at this location, which historically had happened in the past. In fact, the last time they had added this 3-foot overflow pipe, apparently the whole road had blown out. For the long term, for the next 100 years, hopefully this site will have plenty of capacity to handle the water and to allow the fish and other aquatic wildlife to move freely up and downstream.
With the properly sized opening, the natural channel now continues uninterrupted under the bridge and can adjust according to storm intensities and sediment transport.